Hello, my name is Ajaz. I'll be your instructor for Echo 1010. First of all, let me start off by saying welcome to U of T. I have already met the MFE class. They've been here since July 27th, and hopefully I'll get to meet the master students quite soon. So we begin with lecture A-1. This is Echo 1010 is a mandatory course for all incoming MA and MFE students. It's meant to be a refresher course in the sense that it is supposed to bring back memories of math, probability stats, and econometrics that you should have learned in college. But it's also a way for you to shake off that rust. I myself haven't been a year since I taught this course. Uh, had some issues doing some making slides. So as time goes by, you do become rusty. So hopefully the next 3 weeks of really intense math camp will shake off that rust. And most importantly, it is a way for you to get to know your classmates, form groups, because it is going to be quite intense. And this is a as good a time as any other to form friendships. The course. So my name is Ajaz. I prefer that you call me Ajaz. Here's my email address. Because we're in the midst of MFE orientation until mid-September, which involves, and also which also involves, internships for the MFEs, I'm very busy. So I prefer that you don't contact me unless it's an emergency. The person you should be contacting is a TA. He's wonderful. A PhD student named Tommaso Alba. He's from Italy. That's his email address. I believe he's going to hold office hours once a week. And when it comes to lectures, I'll be recording lectures online asynchronously, which means you'll never see me. Tutorials are going to be held synchronously. And the way it happens is, starting on Tuesday, the course formally begins on Tuesday, August 18th. You're going to spend that day listening to this lecture, and then you'll be told what homework questions to prepare. I'll talk about it in a few minutes. And then, of course, starting Wednesday, every single day, weekdays, you'll have tutorials 2 to 4 p.m. Eastern Standard Time. The only exceptions are Friday, August 28th, when you have a test, September 4th, when you have a test, and Friday, December 4th, when you have a test. Tests. This is not a course where you get A, B, C's, and D's. Well, in grad school, in order to pass a course, you must get B minus or higher. C plus in grad school is a fail. But Echo 1010 is a simple credit, no credit course, pass or fail. There are 3 tests in this course. In order for you to pass this course, you must pass exactly 2 out of those 3 tests. Where it should be stressed that test number 1 and test number 2 are mandatory. So you can't just skip test number 1 completely and then try to make up by taking test 2, test 3. You must take test 1, you must take test 2. Failure to take either test 1 and or test 2 will result in automatic failure. So out of those 3 tests out there, you must take test 1, test 2, and you must pass at least, well, exactly 2 of those tests. And the way you pass this is that each test has to be done individually. So you have to score 70% on each of those 2 tests. Here are the dates, all on Fridays. Here are the times. These are tentative. The actual times might be 10 o'clock in the morning till 2. And the locations for these quote unquote exams are going to be online. Please notice that anything is subject to change. And here are some examples for you as to how you can pass or fail the course. So, for example, the best optimistic outcome is you get at least 70% of the first test, which is math, at least 70% of the second test, which is math, stats, and metrics, and then you're done. And then, of course, these are the other possibilities which you can read on your own. It is extremely important that we abide by the code of conducts, and it is your responsibility as a student to read the code of conducts and so forth. You cannot, U of T does not forgive Excuses such as "I didn't know what the contract was." It is your responsibility. You should know what constitutes cheating and what doesn't constitute cheating. Uh, One of the things you will find out in your TA training is at U of T, you cannot, for example, what does count as cheating is anyone who has a cell phone anywhere around them. Your cell phone has to be in a bag. Moreover, that bag cannot be near your desk. So you'll see that at U of T when you have exams, all the bags are in the front of the room or the back of the room with your phone inside. It's a separate story, so how lots of Louis Vuitton and Chanel bags get stolen, but that's a different story. To take those exams, we need some prerequisites. You need to have a laptop or a computer or tablet. That's the device that you're going to use to access the exam questions. Therefore, you must have internet connection. You'll need a camera because we will proctor you remotely. You'll also need a mic and speakers. Obviously, to get the test, you need access to U of T emails. I assume everyone here has it, and you should please download the Zoom app, not on the web, the app itself. Under no circumstances are you going to use headphones during the exams. You will also need a separate device, uh, right, to with a camera to quote unquote take pictures of your exam. So what's basically going to happen is we're going to email you the exam. You can look at the exam on your device, and then what you're going to do is when you're done, you're going to upload pictures of your answers. I highly recommend something called the Cam Scanner app. It takes beautiful pictures of your handwriting. You'll be amazed at how awful some people's handwriting is. I'm not an exception, but it's a good idea to download that app. You will need your U of T student ID, literally the ID card, and a user ID. Please make sure your user ID is active. You'll need plenty of paper. Recommend 8.5 by 11 inches pencil paper, and obviously no other person can be in the room. What's going to happen is shortly before the test, we're going to send you an invite for a Zoom session. You get onto Zoom, and by the time the test starts, and of course we should be able to see you, but sadly we can't hear you. Well, actually, can hear you, but I just don't want to hear you right now. So your video should be enabled. Right away, you'll be asked to upload a copy of your U of T ID through CrowdMark. And then about 15 minutes later, you will receive an email with a unique link to your IP to your CrowdMark test. Please note that the system will track when somebody has clicked on the test link, so you can't come back and say I never got. You can't actually get the link, click on it, and then claim afterwards you had problems. We've got lots of people cheating this way, so the system does know when you've opened the link or clicked on it. It also records your IP addresses. Exams 1 and 2 are open book, but you must of course work on your own. We will monitor you through that Zoom session. And of course, at the end of the exam, you should leave enough time to scan and upload your answers. It's a rule that if there are several questions in the test, which there will be, the first page of the answers must have your student ID, actual ID itself, the picture. There are circumstances under which you may not be able to take a test. Please read the slide carefully. Long story short, you must let us know right away if you can't, if you're going to miss a test. You must give us a legit medical note. In the past, I've received notes from massage therapists claiming the grad student is sore. Well, of course you're sore. You're a grad student. That's the whole point of being a grad student. So no, massage notes from massage therapists saying you're sore is not a medical note. So it has to be something obviously more substantial. And if we agree with your medical note, we will allow you to make up the exam in 2 weeks. Course materials. You will look at the lecture slides and problem sets which are posted on the course website. Here are some highly recommended materials. For example, I really like Martin's math tutorial. And for probability and stats, I highly recommend Drake and Hogg, McKean, and Craig. We'll begin with math. Within math, we have all these topics. I'll start with the vectors, which obviously, as you know, are quote unquote the foundation of linear algebra. One thing about grad school is that vectors in grad school don't behave or are not really what you remember from quote unquote high school. In high school, the typical story was to show vectors as an arrow. The story could be that there's a particle moving through two dimensions. Here is the trajectory. You can see that it took uh, it's sort of much faster over here and much slower over here. And someone could ask you, tell me the position and the direction of movement at a particular instant. For example, when the particle has reached on the x-axis a value of 5 and on the y-axis a value of 3. So you're looking at coordinates 5 and 3. You'll notice up here that I have set bold in x. The bold x is a vector. It records the x coordinate and y coordinate. Since we're not in the realm of matrices, it doesn't matter whether you write this as a column or as a row. When you do matrices, it does matter. But right now, we're not doing matrices. And I will tell you down the road how one knows at a deeper mathematical level how one knows you should be working with vectors or with matrices. Right now, I can record the location 5 and 3 in a number of ways. Here is 5, 3. I take an arrow from the origin to this point, and this shows me the precise location of this particle and the direction of movement is going over here. The location is the x coordinate is 5, y is 3. I can write it in a column, I can write it in a row form, and either way, I can use a bold x to denote this. Now, therefore, I can write again the location without having to say x coordinate 5, y coordinate 3. I can say 5 and 3, which is understood that the location right now is 5 on the x-axis, 3 on the y-axis. Again, going back to high school vector arrow vectors, you may remember this picture. You kind of want to pay attention to this one. You're being asked to add two vectors, x plus y. Notice I did not say y plus x. X is 5, 3, y is 1, 6, and I'm asking you to add x and y. The way it works is addition is that quote unquote you take the tail of one vector and put it on the tip of the other vector. So what that means is if we actually carry out the calculation, you know the answer is when you add x plus y, it should be 6 and 9. But what did I mean by put the tail on the tip? Using a classic parallelogram trick from high school, you must have remembered this like this. Notice that the answer x plus y is gotten by as follows. You could have imagined going from here and then you could go over here. What that means is if I said x plus y, I could displace y or translate over here. So x plus y gives me x plus y. So you should ask yourself, how would this trajectory have changed, x plus y, had I asked you to do y plus x? It's pretty obvious. When you multiply an arrow vector by a scalar, a number, here's the vector x. In this case, I'm multiplying by number 3, so the effect, of course, is to stretch it out. Had it been minus 3, I would have reversed direction and gone the other way around, right? So we know that when you quote unquote add vectors, you get a third vector that's something else. When you multiply a vector by a number, you get another vector that's always along the same quote unquote line. Here's your first homework question. Please look at problem set number A. Do question number 1, 2, 3. These are high school vectors. Let's now do grad school vectors. Ready? Here goes. In grad school, when you talk about vectors, vectors are objects that live in a space. So let's start a bit slowly. A vector space is a collection of objects, which are called vectors, and this space, this collection of objects, is going to be a vector space and its members are going to be vectors as long as a couple of things are true. First, two rules, one for adding and one for quote unquote multiplying by number must summon. These are definitions. That means you are free to define summing the objects any way you want. Remember, a vector space is a collection of objects. This could be anything. You need to come up with a rule for how you add those objects, and you need to come up with a rule for how you take a number and multiply an object. Once you have a rule for adding two objects, and once you have a rule for what happens to multiplying a number to an object, then as long as the following 9 properties are true of all members in this set, that would be a vector space, and its members would be vectors, which are what? First of all, let's get used to some notation. Bold X, Y, Z are members of this set. They're vectors, they're bold-faced. This thing that looks like I don't know, well, it looks like this. This is the mass symbol for n. So X, Y, Z are in the set V. Baby A, baby B are scalars, numbers. So somehow you define a rule for adding vectors and a rule for multiplying vector by a scalar. You'll see an example in the next slide very soon. Once these rules are done, if you apply these rules and you add two objects, those two objects must remain in the space. If you now add two objects and multiply by a number, it's the same thing as taking each of them, multiplying by a number, and adding them up. If you add two scalars and then multiply by an object, same thing as, of course, taking each of the scalars and multiplying by the same object. This is pretty self-obvious. It doesn't matter whether I do A into B times X, or I first multiply A times B and then multiply X. This is kind of nice. It's very counterintuitive. It looks obvious, but actually it isn't. X plus Y should give the same answer as Y plus X. In other words, if I put the tail of Y on the tip of X, I should get the same answer as putting the tail of Y. Oh, Jesus, sorry. Let me try to start one more time. If I put the tail of Y on the tip of X, I should get the same answer as putting the tail of X on the tip of Y. You remember that in the previous exercise. Remember that when I asked you to do parallelograms and see what would actually happen if you did Y plus X and X plus Y? This means that the order of addition does not matter. This is more subtle than meets the eye. There exists some object in this space that is called the zero. It doesn't have to be all zeros, by the way, in the numbers, but it's a quote-unquote null vector, which we call zero, which has a property that when you add it to any object in your collection or in your set, you get back that number. And once again, I stress that this does not have to necessarily consist of the number zeros. We'll see in a few minutes why. For any object that you can think of, there's another object called minus that object, which has a property that when you add the first object plus the minus object, the inverse, you get back the zero. So notice the zero has to be defined first, and then this comes later. And 1 multiplied by this object should give back the same object. So I just want to let you know that these are, again, the best way to think of vector spaces are, there are rules for summing vectors, multiplying vector by a number, and then there are these other quote-unquote laws or features that you need. Various textbooks present these features and laws in different ways, but they all are fundamentally the same. Examples. Supposing, remember, a vector space is a collection of objects. So let's take the objects. Let me take all n Nancy by Mary matrices. So for example, n could be 3, m could be 4. Take every single 3 by 4 matrix in this universe, anything that you can think of. You should be able to verify, and this is also, I believe, in a problem set, that Using the rules of addition and scalar multiplication that you remember from linear algebra, you can soon verify the space of 3 by 4 matrices, or for that matter, n by m matrices is a vector space. Take a function called polynomials. These are coefficients a0, a1, a2, and so forth. As a0, a1, a2 take different values, you get different functions. Take every single polynomial function out there using the familiar rules of algebra, addition in algebra, and scalar multiplication in algebra. You can show that the collection of all polynomial functions is a vector space. This is more devious. Here's a vector space that has one element, z. You don't know what this is. It could be an ice cream, umbrella, numbers, who knows. And now I need to give you two rules. Here's a rule for adding objects. So I tell you that when you add two objects, you get the same object back. Why did I not say x plus y? Think about this. Why did I have to say z plus z? Must be equal to z. And when I take a number a and multiply by z, with this object z, I get back z. You should play around with those laws that you saw in the previous slide and show that this is in fact a vector space. To do this, you will reduce these rules and you will show these 9 properties hold. Good luck. Here's a crazy vector. Two numbers sitting in R2, xy plane. Again, I need to define laws of addition and scalar multiplication. Now, things are upside down. Normally, when you add quote unquote two pairs of numbers, it's traditional to say x1 plus y1. But this time, you're free to define addition any way you want. So we define addition as this one, x1 plus y1. And I artificially stick in the number 1 here. And when I add the second coordinates, again, I stick the number 1 here. If you give me a number a and multiply by this pair x1, x2, I get back the first term is a times x1, and then add an a and subtract a 1. That's my rule for scalar multiplication. You would have normally said a times x1. Those days are long gone. It's grad school. You can define things any way you want. And now I define scalar multiplication as a times x1 plus a minus 1. And things over here as well. However, lucky for you, these are not the vector spaces we'll be working with. We'll be working with vector spaces in real numbers. What are real numbers? Let's start with the real line. The real line goes from minus infinity to plus infinity, contains every single number out there. You could say R1 to show that you're looking at a set of numbers, just one number at a time. We say R. So any one point in the real line is a number x. R2, these are a set of two numbers, i.e. xy plane. So any point in R2 is a pair of numbers. One tells you the x coordinate, the second one tells you the y coordinate, quote unquote. R3, 3 dimensions. Any point will consist of the x, y, z coordinate. Examples. Here's a number 5. It's an element of R, quote unquote, 1. 3, 5 is an element of R2. It's a point in R2. And 25, 50, 30 is a point in R3. These are simple elements or points. How do you go to higher dimensions? Let n Nancy be any positive integer that's bigger than or equal to 1. And now we look at Rn. These are now n dimensions. N dimensions now means that if you want to identify a point in Rn, it would actually have to have n Nancy coordinates. And since you're not working matrices, you can write them as a row or as a column vector. Either way, it's the same thing. These are the coordinates of that point. The ith coordinate or component is given by x baby I. Please notice the difference between bold faces and no bolds. Let's start and see if we can define the set of all real numbers. N can be any number bigger than or equal to 1, integer. So maybe the real line, maybe XY plane, XYZ plane, 4 dimensions, 5 dimensions, 6 dimensions, n dimensions. For this to be a vector space, two things must be true. Someone has to give us a rule for summing objects and for multiplying a number with the object. Here we go. We are going to say, give me any two elements in Rn, for example, x and y. I'm going to define the sum of x plus y to be the following. Take each, if you want to add x plus y, add the first coordinates, add the second coordinates, add the third and the coordinates, and you get this. Notice that by definition, the result has to be in Rn. You should think about why that's true. How do you know it is in Rn? Why wasn't it outside of Rn? Scalar multiplication. Now, we take a number, baby t, and now we multiply by a vector. What happens? Our rule is you're simply going to pass it through. So t times a vector x is t multiplied by each coordinate of the vector x. And now remember those 9 features? Here are those 9 features. So I won't go over them. You should compare these 9 expressions with the ones you saw a couple of slides back. You should obviously do these questions in the homework. But then, doing this will give you a good sense of what these laws mean. It's often, sometimes, you need to plot vectors. So I'm sure every single person here knows Wolfram Alpha. Yes, Wolfram. I believe he got his PhD before he was born in physics from Caltech. He has a lovely website called Wolfram Alpha. Sorry, kids, it's not Instagram. And you can do things like this. So, for example, you can use it to plot a vector 10 in R1. I'm doing this on purpose because when you see exams, sometimes the number 10 can appear in 1 dimension or in 2 dimensions. So right now I'm giving 1 dimension. I'm giving you 3, 5, and I'm telling you sitting in R2. So here's the vector 3, 5. And that's the command you use. You click on this to actually go to the command. I now want to make a vector 15, 40, 60. Here we go. Right? Some of you might say, wait a second. Why am I calling these vectors where these are simple, where they still look like arrows? They are arrows. The difference is it looks a bit like high school because they're arrows. But what I did in the previous slide was I defined summation rules, multiply by number rules, and those 9 properties for these arrows. Hence why I can call these things vectors, because I know Rn is a vector space whose members are vectors. Now, let's start. Here's x plus y, your familiar high school problem. Notice I'm using the definition of summations that we had some over there. So x plus y. And again, using the parallelogram interpretation, since you want x plus y, you can think of it as x displace y, right? That would be over here. Sorry, my bad. I should have been over here. Here is x. And so what you want to do is you want to get x plus y. So you get x plus translated y. So essentially, x plus y gives you x plus y. What would actually happen if you did y plus x? So you don't want to go this way because that would be x plus y. You want to go y plus x. So you can see what actually you have to then do is if you want to use a parallelogram interpretation, you would have to translate x over here. And now you can see y plus x gives you y plus x. Pretty neat. Of course, what happens when I multiply by a scalar? Nothing new. If I multiply a positive number, I stretch that vector. If I multiply by a minus number, I reverse direction. Of course, whether I shrink or stretch depends on whether the number is bigger than or less than 1. Now that I actually have what you may call it, now that we know how to add vectors, now we know how to multiply a vector by a number, we can now do subtraction, because subtraction at the end of notice is if someone asks you to do x minus y, of course that's the same thing as x plus quote unquote minus y. And so you can work out the algebra yourself, but in terms of parallelograms, it's kind of you helpful to see that what's happening is the following. Notice that if you want to use a parallelogram interpretation, what you want to say is something like the lines of this. X minus y plus y is equal to x. So if I translate y over here, x minus y plus y is equal to x. That's your good old parallelogram interpretation. And now here, you're doing a parallelogram interpretation of y minus x. So we know that, quote unquote, y minus x plus x must be equal to y. So if I translate x over here, I can see the parallelogram interpretation. Y minus x plus x is equal to y. Some special vectors. The zero vector. So notice the boldface here. It means that it's sitting in Rn, and therefore it has n coordinates. Each of them are equal to 0. Sometimes I'm lazy, textbooks are lazy, profs are lazy. You, of course, will never be lazy. So instead of saying boldface 0, you could simply say plain 0. Here's the quote-unquote counterpart of the number 1 in vectors in Rn space. We could use the notation in, subscript n, to show that these are ones, there are n number of n1 terms, or we could use the number 1 bold, as you see over here. Here's an example of y3. It's three-dimensional one vector. Each of the coordinates is 1, 1, 1. This is critical. Without this, you're not going to pass the course. These are unit vectors. So in Rn, what that means is, by example, in R2, two-dimensional space, there'll be two unit vectors. One on the x plane, so there'll be a vector of length 1 along the x-axis, and a vector of length 1 along the y-axis. In R3, there'll be three unit vectors, each of length 1. In what sense? There'll be one along the x-axis. Here's 1, 0, 0. One on the y-axis, 0, 1, 0. One on the z-axis, 0, 0, 1. So in general, the unit vector will have this property. The ith location will have the number 1 for numbers going to 1 through n, and all other values other than I will be equal to 0. So for example, here you can see I is equal to 2. For I is equal to 2, E2 is 1, E1, E3 are 0. Let's do a linear combination of a set of vectors. Fancy words for give me a set of vectors, a collection of vectors, and add them up. Someone gives you a set S. Here's a set S of k vectors, meaning that there are k number of vectors, 1, 2, 3, 4, all the way to k. Each of these k vectors is sitting in Rn. Take a close look at the subscripts. Notice 1, 1, 1, 2, 1k. So what you're saying is you're using matrix notation. First row, first column, first row, second column, first row, kth column. Nth row, first column, nth row, second column, nth row, kth column. So these are k vectors, each of them sitting in Rn space. And now I take some numbers. If you're k vectors, you need k numbers. T1 is some number, T2 is some number, Tk is some number. If I now take T1 and multiply by the vector x1, add the number T2, multiply the vector x2, and keep doing this all the way to the kth vector, I get what's known as a linear combination of those vectors. So when you expand it out, what you're doing is you're multiplying the number T1 by the column vector x1, whose elements look exactly like this. T2 times x2, etc., etc., etc. Everyone should be familiar with the sum notation. Notice how you can express this entire expression as baby t's multiplied by bold x's, which are the vectors, all the way from I to k. We bring this up because you're about to see that unit vectors, remember those creatures in Rn, you will have n unit vectors. So they start with 1, 0, 0, 0 something, 0, 1, 0, 0, 0 something, 0, 0, 1, 0, 0, 0, and so we're about to say they are the, notice the emphasis on the, not a, the natural basis of Rn. What does that mean? You're going to show that you can take any vector, for example in R2, and express it as a linear combination of E1, E2. So give me any vector in R2. I can give you that vector in terms of E1, E2, and so that those multiplied by numbers. So here's what we mean. Someone tells you there's a vector x in R2, it's 5, 3. Can you express 5, 3 as a summation in terms of E1, E2? Sure you can. Take a look at 5, 3. I can write it down as 5 into 1, 0 plus 3 into 0, 1, right? Because this will become 5 and 0 here. This will become 0 and 3 here, which will give you 5 and 3. So this, of course, is E1. That's E2. So you've noticed that if someone gives you a vector with the first coordinate x1, second coordinate is x2, you can write down as first coordinate times E1 plus second coordinate times E2. So notice, here's your E1, here's E2. And you were able to somehow do something linear combination to get X. It is a really good time to sit down and say, what does that even mean in terms of pictures? Here you saw I took 5E1. What 5E1 is going to do is it's going to take this vector E1 and stretch it out all the way to 5, right? Because I'm stretching it. 3E2 means that I'm taking the vector E2 and I'm also stretching it, in fact, making it 3 times bigger. So when I take the 5E1, which is not shown here, and I add that to 3E2, which is also not shown here, using the sums of addition, this parallelogram tricks that you saw earlier, you can show that you can get the vector x. So here's a rhetorical question. This little example should show that in fact it is possible to express any vector in Rn space always as a linear combination of E1 through En. So I'm going to say this formally. Give me any vector in Rn. I can always express vector in Rn as a linear combination of unit vectors. Meaning what? I can take the first coordinate multiplied by unit vector number 1, E1, second coordinate multiplied by E2, and keep going. So any vector x can be expressed as a sum, as a linear combination of unit vectors. Exactly as you see here. You should now start, when you go to sleep tonight, you should start to imagine what will actually happen if I chose different values of x1, x2. And you can start to see that in your mind, you have all these unit vectors sitting around in some space. As you give different values x1, x2, x3, x4, you're going to quote unquote generate these all kinds of interesting vectors. And with different values of baby x1, baby x2, baby x3, and so forth, as you generate new vectors, you could start to span some space, right? You can imagine that's going to sort of inhabit or this will be like a flourish of those little vectors, right? So it is in that sense we say that the set of vectors is the natural basis of Rn, and I'll talk about spanning in a few seconds. Exercise over here. Now comes the tricky part. You know that you can take any vector in Rn and always be able to express as a linear combination of E1s through ENs. Okay? I wonder if I can do something else. Once again, give me any vector x in Rn space. But I wonder, can I express this vector in terms of any vectors x1, x2, xn in Rn? I know that I can certainly express my vector x in terms of E1, E2, E3, and so forth. That I know. But now I wonder, can I express them in terms of any vector that I can choose in Rn? And the answer is Well, depends. So once again, to see this, we visit our linear combination of vectors one more time. We look at the concept of linear independence and dependence. This has nothing to do with freedom or lack of freedom, and the basis of vector spaces. Same slide you saw earlier. You have a set of k vectors. Each of them is sitting in Rn. K vectors, each of them in Rn. I know that if I take a number multiplied by x1 plus number times x2, I get a linear combination of those vectors x1, x2, and so forth. And that's what I was saying a bit earlier. As I start to choose different values of, I may have misspoken earlier, guys, I'm sorry. As I choose different values of t1, t2, t3, and so forth, I will then, of course, start to generate different vectors, right? A different vector, and that allows me to then quote unquote span the space. You can sort of populate space with all kinds of vectors consisting of x1s, x2s, x3s summed up. Back to our discussion. I know if you gave me any vector x, I can always express it as a linear combination of the unit vectors, e1 through en. But I was wondering something else. If you gave me something else besides e1, e2, en, you gave me some arbitrary vectors, could I still do this? So, to make it simple, can I, for example, take any vector in R2, xy plane, and express it as a linear combination of any other two vectors also in R2? It says any two, so I know for sure that I can do I can do E1, E2 for sure. But are there any other vectors that also do the job? So before you start looking at this box, think of it this way. Supposing I gave you these x1, x2s, and I ask you, notice that x2 and x2 are at an angle to each other, and since they don't lie on a line, clearly one vector is not a multiple of the other vector. In contrast over here, x1, x2 do lie on the same line, so it must be true that one vector is a multiple of the other. For example, x2 could be twice as long as x1, right? So you notice a big difference here. Let's come back here. I give you x1, x2. Now I ask you, can you somehow combine x1, x2 to generate, let's say, some vector x? And the answer is you should be, because you should be able to stretch, reverse, shrink x1, stretch, shrink, reverse x2, and add the modified x1 and x2 in some way to get x. Right? You kind of form a parallelogram if you want to, right? With the appropriate, you know, again, you can expand it, shrink it, reverse it, sending x2. And if I take that linear combination, I should be able to get x. So you can see that the answer is if you gave me x1, x2, I am able to find, I can express any other vector as a linear combination of x1, x2 as long as x1, x2 are not at an angle to each other, not on the same line. And when two vectors are at an angle to each other, when they're not on the same line, they are said to be linearly independent. So when can I take a vector x, express as a linear combination of x1, x2, when those x1, x2s are linearly independent, i.e. at an angle to each other. Take a look at this one. Now x1, x2 are on the same line. They're not at an angle to each other. If I were to multiply x1 by any number, I could shrink it, I could expand it, I could reverse the direction, but it'll always be along that line. Same goes for x2. So whatever modification you do to x1, whatever modification you do to x2 is always going to be along this line. So the question is, if any modification of this x1 and x2 is always going to be this line, how can I take a linear combination of those modified x1, x2 and somehow get x which is on a completely different line? It's impossible. So anytime the x1 and x2 vectors are on the same line, there is no way you can combine them in any way whatsoever to get a third vector called x. So in plain English, give me two vectors x1, x2. If I can find I can express any vector x as a linear combo of x1, x2, as long as x1, x2 are at an angle to each other, i linearly independent. And I cannot do that if they are linearly dependent, i on the same line. Examples. Someone asks you whether you can take the vector x5, 5, 3, this x right here, and express it as a linear combination of 2, 1, right here, and 4, 2. Well, no, because remember that, what does the linear combination say? It says take a number, multiply x1. When I take any number multiplied by x1, I will always move along this line right here, along the same line as x1. When I take a number t2 and multiply by x2, I'll again always generate new vectors always on this line. So I've generated a new vector t1x1 on this line. I've generated new vector t2x2 on this line. And when I add the two, they must also be on this line. It's physically impossible for that to be equal to this. So you cannot generate 5, 3 from a linear combination of x1, x2 because these are x1, x2 are linearly dependent, i.e. on the same line. And notice what must be true is that one vector must be a multiple of the other. In this example, x1, x2 are at an angle to each other. Here's x1, here's x2. I wonder if I can find a linear combination that combines x1, x2 to generate this vector x. Well, yes, I can. If I were to multiply x1 by a number, t1 times x1, I would get something that's along this line. If I were to multiply x2 by t2, t2 times x2, I'd get something this line. So with a clever choice of t1, for example, you can see that if I chose t1 to be 9 divided by 5, I would stretch x1. By a clever choice of t2, for example, if I chose t2 to be 1 over 5, I shrink x2. So it goes from x2 to 1 over 5 x2. And if I now take this modified x1 and add the modified x2, by using the parallelogram trick, I get the vector x that I want. So I can express any vector in R2 from x1 and x2 because x1, x2 are linearly independent, i.e. they are an angle to each other. So how do you know if two vectors are independent or dependent? You don't want to be drawing pictures in your test. It's grad school. Those are for undergrads. By example, I'll prove this. Once again, you know that when vectors are linearly independent, you can combine them to get any other vector. When vectors are linearly dependent, you cannot combine them to get a third vector. So without having to draw the vectors all the time, how do we know they're linearly independent or dependent? In this picture, x1, x2 are along the same line, they're linearly dependent. In fact, notice that x2 is exactly twice as much as x1. So in general, if any two vectors are linearly dependent on the same line, what must be true is that one of these vectors must be a multiple of the other one over here. You should obviously not take this notation literally because the alpha here is not the same as the alpha there. But mathematics does not care because as long as you understand, this expression simply says x1 is a number multiplied by x2. So it's understood that they're on the same line. I now bring this expression to the left. And I notice that this is for all practical purposes the number 1. That's for all practical purposes the number minus alpha. So notice that this is in fact a linear combination of x1, x2, where t1 is 1, t2 is minus alpha, right? So notice how the question was, let's slow down a little bit. Are x1, x2 linearly dependent? Notice that I have been able to find a linear combination of x1, x2. This one right here, 1 times x1 plus minus alpha times x2, which is equal to 0. And notice that alpha was of course not zero because that's why they were. But the fact they're on the same line, you knew alpha had to be a number different than zero. So you have taken two vectors, you found a linear combination that makes the whole sum equal to zero. So the answer is, how do you know x1, x2 are linearly dependent? What you do is you set this expression up. Take the linear combination t1 x1 plus t2 x2 is equal to 0 and ask yourself for what values of t1 t2 will this be true. If you can find at least one t, baby t, that's not equal to 0, that means x1 x2 must be linearly dependent. So you should think about this a little bit more carefully because people are starting to probably get confused about, wait a second, I was doing some other t1 x1 plus t2 x2 before. What you were doing before was completely different. That was asking whether you can somehow do a linear combination of x1 x2 to get some vector x. But what you're doing here is completely different. Even the symbols that I'm using are the same, the context is completely different. Now what you're asking is, by example, you can see any linear combination of x1 x2, right? Sorry, not any. If there is at least one linear combination of x1 x2 such that the whole sum is equal to 0. If you can find a t1 and a t2 where at least one of them is not 0 so that the whole sum is 0, those x1 x2s are linearly dependent or on the same line. By the reverse logic, if two x1 two vectors x1 x2 uh, are linearly independent, then one cannot be a multiple of the other. And because one is not a multiple of the other, when somebody asks you to look at this expression, says, tell me, can you find some t1 and t2 where at least one of them is not 0, such that the whole sum is 0? The answer is no, because you already know that one vector is a multiple of the other vector. So the only way that this sum can be 0 is if each of the t's are equal to 0. So let's go back to the previous slide. It is possible for this sum to be 0 when you choose the value t1 is 1 and t2 is minus alpha. There is some non-zero values of t1 and t2, so the sum is 0. That's why they're dependent. Here, the only way for the sum to be 0 is if the t1s and t2s are individually equal to 0. So you now have a quote-unquote test. You now know the answer as follows. Can you express any vector in Rn space as a linear combination of n other vectors? You can do so if you knew those x1, x2s, xn are linearly independent. And for that to happen, how do you know these are linearly independent? All you have to do is ask yourself whether this is true. Set up this sum, t1 times x1 plus t2 times x2, all the way tk times xn. Remember, there are k of those vectors right there. If the only way for the sum to be 0 is if each of those numbers are equal to 0, you say those vectors are linearly independent. And if you have found at least one t that's not 0, such that the entire sum is 0, those are linearly dependent. And of course, the only way to sorry, reinforce this is by doing a problem. It literally boils down to solving this equation and looking for values of t's. Let me jump ahead and sort of connect this to something that you probably saw in matrix algebra. I will come back to this in the future, but right now I'm going to jump ahead a little bit. You probably remember from good old undergrad that there are many models in economics that consist of linear equations that can be expressed in the following matrix form. A is a square matrix, X is a vector, B is a vector, right? And you remember that oftentimes you also solve for X. These are the variables. And to do so, you had to quote unquote invert the matrix. But you also remember it's not always possible to invert the matrix. Can we use the last few slides and see when you can invert a matrix. I want to answer the following question. When is A square matrix A invertible? I'm jumping ahead to matrix algebra. Again, I have the subscripts are first row, first column, first row, nth column. I'm going to label the column vectors as x1. Here's a column vector number 1, column vector number 2, the nth column vector. And so notice that this matrix A is in fact not only a collection of n by n numbers, but n column vectors, each of them sitting in Rn. I now ask you, you of course know the system Ax is equal to B, but I ask you now to tweak it. Keep the matrix A as it is, A. Instead of now talking the variable x, let's call them variables baby t. And now instead of b's b, let's call it 0. This is a modified, a different version of the ax b is equal to system. There's a very particular system right here. You want to know if the matrix A sitting right here is invertible or not, using what you saw in the last few slides. What you do is you set up the system A times t is equal to 0. This is known as a homogeneous system. Jumping ahead to matrix algebra, I know that if I multiply this out, I will get what you see over here, right? Uh, Actually, I think there might be a typo. Actually, no, that's fine, I think. We'll worry about it later. Okay, fine. Um, so you have this linear combination over here, see, because so it is a typo, no? So first row times this column, it should be A11 through A1n. Sorry, guys. Right? This should be a n1 through t1. So this should be a n1, and that's perfectly fine with it. Now, what I'm going to do is I'm going to label these column vectors x1, x2, xn. I hope it's starting to look familiar. See, you have a linear combination of x vectors. That must be equal to 0. You want to now get some insights into what you just said right now. You wonder what must be true for the matrix A to be invertible, utilizing what you learned in the last few slides. You artificially set up the system square matrix A multiplied by T is equal to 0, homogeneous system. And you know it looks like this. It's a linear combination of vectors x1 through xn. Let's start here. If indeed A was an invertible matrix, then you should theoretically, or if it was invertible, you should be able to perform the following operation. You should be able to multiply both sides by the inverse of the matrix A. You remember that this will then become the inverse matrix. That'll give you the t vector. And inverse multiplied by 0 gives you 0. So this says if the matrix A was invertible, all these t's should be equal to 0. But voila, what does that mean? If all these t's equal to 0, that means this t1, t2s, tn's should all be equal to 0. So you've just again verified what you saw earlier. For a matrix to be invertible, the column you need to actually therefore for A to be invertible, you need to actually have the column vectors be linearly independent. And you know this because the only way this linear combinations can be true is if each of the t's there are equal to 0. But if it's not invertible, I can't proceed any further. I cannot multiply this by any inverse, not exist. So the fact that you have a square matrix multiplied by something is equal to 0 means that at least one of the t's must not be 0, which must mean they are linearly dependent. So that means the column vectors of A must be linearly dependent because at least one t is not 0. I hope this isn't getting hard. We're just getting warmed up, by the way. So, you've shown that a matrix A, square matrix A, is invertible, i.e. non-singular, if its column vectors are linearly independent. Sadly, since most textbooks talk about square matrices X being invertible, I'm going to restate the exact same result. A matrix X, which is square, is invertible if its column vectors happen to be linearly independent. How would you check it? You would check if T1 times first column vector plus T2 times second column vector plus Tn times nth column vector is equal to 0. If the only values of t's are zeros, those column vectors have to be linearly independent. Let me give you some insight into what invertibility independence means. Supposing you're given a very simple, cute baby's equation system. So simple. A true story. A number of years ago, we used to have a diagnostic test in math camp, and we would give triple integrals, all kinds of weird stuff, and people would have no problems doing it. And one time we gave them this simultaneous equations, and about half the class couldn't do it. Not because they're stupid, but because you're out of practice. I want to show you there's a nice insight into simultaneous equations and what you just learned about invertibility and independence. I want to show you that you can solve this by two ways, the row method or column method. Almost everyone has seen the row method back in elementary school, uh, but not the column method. To show you what these are, notice that you can express this system in terms of the matrix system AX is equal to B. The row method. The row method says take these two lines, these right here, you can see I plotted them. Here's your 2x minus y is equal to 1. Here's your x plus y is equal to 5. Notice that they're intersecting, so that means there is a solution. So here's a graphical intuition. By the row method, it means that you solve these two equations simultaneously. Most of you will probably want to isolate one of the variables. So for example, you might isolate y from here, y from there, set them equal to each other, and in 2 seconds you will get the answer x is equal to 2, and then you will find out y is equal to 3. So the row method says, imagine these two lines, uh, they since they intersect, you can isolate x's or y's, solve for them, and get values. So the fact that you actually have a solution to the system means that you were able to solve for the values of x and y. X is 2, y is 3, which means intuitively, behind the scenes, that matrix had to be invertible. But if that had to be invertible, that means this column vector 2, 1 and this column vector minus 1, 1 had to be linearly independent. This could be a juicy test question. How could you further prove that these are linearly independent? You would show that t1 times this vector plus t2 times this vector can only be 0 if t1 and t2 are each 0. But let's go a bit deeper. Another way to solve the system is by something called the column method, which looks like this. Take what you saw right here, and now look what you've done here. Here's, you take the x's out, see? This becomes 2 and 1, plus y, here's your minus 1 and 1, is equal to your 1 and 5. Now, I know from the previous slide that a solution exists. I knew that x was equal to, what was it equal to? I forgot. X was equal to, I think it was equal to, let's go back, 2 and 3. So I know that x is equal to 2 and y is equal to 3. Agree? So that means that you knew this matrix was invertible. And as we just said a few seconds ago, that means it implies that the column vectors 2, 1 and minus 1, 1 are linearly independent. But where are these column vectors? Voila, I present to you, here's a column vector 2, 1, 2, 1, 2, 1. Here's your minus 1, 1, minus 1, 1, minus 1, 1. And now what you're saying is these two vectors are linearly independent. And of course, they're linearly independent. That means that the only way the following equation can be true is that the baby t's are equal to 0. We'll stop here and start with this topic for the next lecture.